Write down the formulae for the following. Sodium nitrate, Na is sodium, nitrate is NO3, it has a valency of 1, and therefore the formula for sodium nitrate is simply NaNO3. Potassium permanganate is K, potassium permanganate is MnO4 with a valency of 1, and potassium is in group 1, so it has a valency of 1, and therefore the formula is simply KMnO4. Write down the name of the following chemical formulae. The NH4 is ammonium, and chlorine changes her name to chloride when she bonds. Iron, Fe, and oxide. However, you need to give iron stock notation, so draw it out. Iron, there are 2 Fe's. There's 3 oxygens in this, each oxygen having 2 valence arms, and you can see that the 3 oxygens and 2 ions from the formula. Therefore, how many arms must that ion have in order to connect over here? It must have 3 arms. So you're going to have 1, 2, 3 over there. Study the substances below and select one which meets the criteria for each statement. Firstly, what we have here is we have a polar covalently bonded molecule held together by hydrogen bonding in the lattice. Carbon, you know the 3 allotropes, or 4 allotropes rather, of carbon: graphite, diamond, coal, and Buckminster fullerene. Potassium chloride is a metal and a non-metal, so you have got an ionic bond, and methane is your polar bonds with your non-polar overall molecule due to the symmetry. Consists of polar covalent molecules, therefore, is your water. In the solid and liquid phase, the molecules are held together with hydrogen bonding. It's your water again. A solid allotrope comprises of an atomic lattice, all bonded together. That is your carbon. It's diamond. It is covalently bonded throughout. Dissociates into ions. The only one that has ions is KCl. Conducts electricity when melted into a liquid, but cannot conduct as a solid. That is also a characteristic of an ionically bonded substance. Below is a graph showing the boiling points of various hydrides. Hydrogen fluoride, ammonia, and water have much higher boiling points than the trend would predict. This is due to hydrogen bonding intermolecular forces. Briefly explain what properties of nitrogen, oxygen, and fluorine cause this anomaly in the boiling points. Also explain how those properties result in such strong intermolecular forces between those particles. You need to say that nitrogen, oxygen, and fluorine are small and that they have a high electronegativity. The high electronegativity means that they will have strong dipoles, and those strong dipoles cause strong intermolecular forces. And then the smallness means that they can pack close together, and that also strengthens the intermolecular forces. A solution of potassium sulfate is known to have a certain concentration. Write the chemical formula for potassium sulfate. Potassium has a valency of 1. Sulfate has a valency of 2. Potassium, you need another potassium, so it's K2SO4. K2SO4. What mass of potassium sulfate is present in 50 centimeters cubed of the solution? First, I need to get the number of moles that are in that solution. The number of moles in that solution is number of moles is equal to concentration times volume. The concentration is 0,02. And the volume is 0,05. I need to convert that 50 centimeters cubed into decimeters cubed, so it becomes 0,001 moles. And then the question is, what is the mass? Mass is equal to number of moles times molar mass. So that is going to be equal to 0,001. And the molar mass of potassium sulfate is going to be 174, which is 39 plus 39 plus 32 plus 16 times 4. And when you multiply that out, you land up with 0,174 grams. What volume of the one solution would be required to make up a slightly different solution? You'll remember I like to put it into little boxes, and we go. The number of moles is what we're interested in. I have got the concentration of one of the solutions, and I've got its volume, which I'm going to convert straight away into decimeters cubed. And I can work out the number of moles. I have also got, I'm asked for the volume here, I've got the concentration, and I will get the number of moles in a second. So first let's get this number of moles, and the number of moles is going to turn out to be equal to concentration times volume, which is going to be equal to 0,015 multiplied by 0,25, and my number of moles turns out to be equal to 0,00375 moles. I take that number of moles and I put it into the other container, or I got it from the other container actually, and now if I'm looking for volume, volume is equal to number of moles divided by concentration, which is 0,00375, divided by the concentration of the first solution, 0,02, and we land up with 0,1875 decimeters cubed. It doesn't say how much water has to be added. They did ask me to get how many, this is going to be, decimeters cubed. If they did ask me to work out how much water had to be added, I would have needed to have subtracted it from the 250 centimeters cubed, and I also would have had to have converted one of them into either decimeters cubed or centimeters cubed. A sample of calcium carbonate was reacted with dilute hydrochloric acid in a closed container. The carbon dioxide gas produced was collected and occupied a certain volume. What is the number of moles of carbon dioxide? So the first thing I'm going to do is I'm going to say number of moles is volume over molar volume. They've told me the volume. I was given in decimeters cubed divided by molar volume, which is 22,4, and I land up with 0,015 moles of carbon dioxide. The number of carbon dioxide molecules, number of particles, is equal to number of moles times Avogadro's number. So I take that number of moles, I multiply it by Avogadro's number, and I land up with 9,03 times 10 to the 21 molecules. The mass of calcium carbonate, which reacted with the hydrochloric acid, and now we are into stoichiometric relationships where we are going to need to look at mole ratios. So looking at that balanced equation over there, I'm now looking at a relationship between carbon dioxide and calcium carbonate, and luckily it is a 1:1 ratio. So if I have 0,015 moles of carbon dioxide, I also have 0,015 moles of calcium carbonate. The molar mass of calcium carbonate is going to be equal to 40 plus 12 plus 16 plus 16 plus 16, which turns out to be exactly 100, and therefore my mass is equal to number of moles times molar mass, 0,015 times by 100, and I land up with 1,5 grams. The next one was if the concentration of hydrochloric acid is given, what is the minimum volume of hydrochloric acid for this to run to completion? Again, I'm going to need mole ratios, so I'm going to say what is the relationship between the carbon dioxide and the hydrochloric acid. It's a 1:2 ratio, so instead of 0,015 moles, I have got 0,03 moles. Volume is equal to number of moles multiplied by concentration, 0,03, 0,1, and I land up with 0,3 decimeters cubed. Sulfuric acid is a strong diprotic acid. What is a strong acid? That is that it ionizes almost completely. In water. And what does diprotic mean? It is able to donate 2 protons or 2 hydrogens. Write a balanced chemical equation showing the complete ionization of sulfuric acid in water. So it's H2SO4 in water. Complete means both of those hydrogens need to be donated away, and that means that I'm going to get 2 H3O pluses. In order for that to happen, I better have 2 waters, and I'm going to have the sulfate ion SO4 2 minus. You do need to be able to ionize your acids in water. We've got solution A is something, a certain concentration of sulfuric acid, and the other one is a certain concentration of nitric acid. Which one would have the greater electrical conductivity? It would be the sulfuric acid, because it has got double. You need to say that they're both strong acids, but sulfuric acid has got double the H3O plus ions because it is diprotic in solution. So therefore it is a better conductor. In a swimming pool, calcium hypochlorite dissociates in water to release the hypochlorite anion, which establishes a following equilibrium. Rewrite the above reaction and indicate the acid-base conjugate pairs. So you have got a proton that gets sent over there. So this is your proton donor. Acid 1 turns into base 1, and base 2 turns into acid 2. So those are your links between the two, and you'd need to show those links. Define an amphiolite. It is a substance that can both accept or donate a proton. Provide an example. Water is your most common amphiolite, but you could have said to me the bisulfate ion, the bicarbonate ion. Those are also quite common. We've given a solution of sodium hydroxide. It is titrated against ethanoic acid, and the balanced equation is given. Unfortunately, in this you were not given enough information to be able to solve the problem. This bit of information was missing. We didn't have the concentration, but let's just work it through with it. So the number of moles of acid over the number of moles of base is equal to concentration of acid, volume of acid, concentration of base, and volume of base. And you land up with 1 over 1 is equal to the concentration of the acid is what I don't know. The volume of the acid is given to me. It's 24,5. Concentration of base 0,01, and volume of base is 20. And you could have worked out your answer from there. Would the endpoint be acidic or basic? We've got a strong acid, at least a strong base, and a weak acid. So you're going to land up with a basic endpoint because there is a strong base with a weak acid. What is a suitable indicator for this? It's your phenolphthalein. Spelling still eludes me. If sodium ethanoate, that's that salt over there, were dissolved in water, what would the approximate pH be? Sodium ethanoate is derived from a strong base and a weak acid, and therefore it is going to land up being a slightly basic pH, and that would be anything you could have said to me around about 8 or 9 or something. Not 14, just something a little bit higher than 7.